This conference will now be recorded.
Hello everyone. Last day we have started stereochemical aspects of nucleophilic substitution reaction, and today we will finish it. After that we will compare the features of SN1 reaction and SN2 reaction. These two are basically mechanism, so better we say we will compare the mechanism of SN1 and SN2, and then there will be some related problems, and after finishing that we will start factors that affects nucleophilic substitution reaction. Okay. So three possibilities are there when we are considering stereochemical aspects of nucleophilic substitution reaction. That means if the starting material, that is the alkyl halide, that is the starting material, in general we can write it as Rx. So if this starting material, there is some chiral center present in the alkyl part, then the question of these three possibilities actually arises. Otherwise, there is no such possibility. Fine. So if there is any chiral center present in this alkyl part, these three possibilities are retention, inversion, and racemization. So when a bond directly linked to an asymmetric carbon, that means the carbon with which halogen is attached, that carbon must be chiral. Then only these three possibilities, the question arises. Fine. So the bond directly linked to an asymmetric carbon atom if it is broken, and we know that in nucleophilic substitution reaction this bond between carbon and halogen is broken, and after reaction we get RNU. So that is why this carbon halogen bond as it is broken, and if the carbon is chiral, then three possibilities may be there. So the first possibility is if, let me write it, what is AB. So see, here we have taken one example. This is basically general example. So here the molecule is carbon which is attached to leaving group, and this leaving group is basically halogen, and this carbon is chiral because it is attached to three different alkyl group and one Lg. That means all the four groups are different. So this carbon is chiral. Now what are the three possibilities? The three possibilities is if the nucleophile it is attacking from the back side. Okay, so if it is back side attack, obviously now nucleophilic carbon bond that will be formed, this is in the left hand side. Okay, so this is known as inversion. But if it is attacking from the same side means where already Lg is present, if it is attacking from the same side, which is we call it as front side attack, now there will be retention. Fine. Now if both these processes are going on in same rate, that is 50% chance, if it is there, then you will get mixture of enantiomer. Okay, so inversion is basically where relative configuration of an atom, which atom, this carbon, is changed, but when it is retained, that is not changed, then it will be called retention. Fine. So here A is basically, that is retention is there when A is the only compound obtained. So this is A and this is B, and B is the only compound obtained, that is only product. Then you can call that in this mechanism only inversion is going on. And if 50-50 mixture of A and B are there, that is both A and B are formed and their percentage is 1:1, then it will be ultimately enantiomeric mixture, and that will be ultimately optically inactive because the rotation that you will get from one compound, that will be balanced by the opposite rotation of the other compound. Okay, so that is why ultimately the mixture will not be active. But suppose if it is 60:40, that is not exactly 50-50, then you can expect optical activity. Now when it is SN1 or SN2 mechanism, now actual example we have taken in this box in the right hand side, the example that you are seeing, that is basically the general expression of alkyl halide. But see in this box in the left hand side, now carbon is attached to four different groups. Here we have bromine, hydrogen, methyl and ethyl. Now if we number these groups according to priority, hydrogen will be least priority, so it is 4. Bromine is 1 because it is maximum priority. Then ethyl group is 2 and this is 3. Now the lowest priority group, as it is away from us, under this condition, when you are moving from 1 to 2 to 3, this movement is basically clockwise. So 1 to 2 to 3, this movement is clockwise, so that is why it is R. Now two types of attack possible. Here the reagent that we are using as a source of nucleophile. The nucleophile is actually iodide, I minus. But where from this iodide is generated? It is generated from sodium iodide. Okay. Now the iodide, it can attack front side. So here the front side attack, it is shown here by the gray color. Okay. And the back side attack, that is shown by the black color. Now when it is front side attack, we are getting retention, and here configuration is unchanged. Initially before the reaction it was already R, and now you are also getting R. And if it is opposite side attack, you are getting S, because now this is number 4, least priority, this is again number 1, this is number 2, and this is number 3. So when you are moving from 1 to 2 to 3, okay, sorry, it is 3, methyl group is 3 and ethyl group is 2. So now the movement 1 to 2 to 3, it is anti-clockwise, and that is why it is S, and this is inversion. Fine. So in case of optically active alkyl halides, that is the alkyl halide that you are seeing in this box, that is actually optically active. And when it is SN2 mechanism, what we know in SN2 mechanism, it is always backside attack, that we have already seen in the last class. And if it is only backside attack, obviously inversion will be the ultimate result. But when it is SN1, it is not that you are getting the opposite process, that is retention. No, in SN1 there is a formation of free carbocation, and free carbocation is planar. So both side attack, equal probability is there. So that is why ultimately it will lead to decimization, because both inversion as well as retention, both will take place. So ultimate result is obviously decimization. Fine. So is there any doubt? Should I repeat any part? So now we will compare these two mechanisms and different points we have here. But first see, here RLG, it is nothing but Rx. Just it is written in a different way. And nucleophile, if it is nucleophile, obviously Rx is the electrophile, right? Because nucleophile will attack the carbon that is present in the R group. And that carbon which is present in R group, that must be electron deficient. Why electron deficient? Because X, which is electron withdrawing, that is directly attached to carbon. So that is why here it is written as electrophile, but it is actually alkyl halide when you are considering nucleophilic substitution reaction. And ultimately what you are getting NUR and LG is reduced. Now we are comparing SN1 and SN2, and the first point is rate law. If you consider the rate law for SN1, it is rate constant multiplied by the concentration of electrophile, but you can also write it as K into concentration of Rx. Same thing. And if it is SN2, now another concentration term is also there. It is not only electrophile, that is not only Rx, but nucleophile concentration also you have to consider, and that is why it is bimolecular, and we write the term as SN2. 2 means bimolecular. The second point is reaction energy diagram, energy profile diagram. Remember, in last class I have already drawn the energy profile diagram for SN1 and also for SN2. Now SN2, as it is single step reaction, it is single step reaction and it is two steps reaction. So as it is two steps, so there must be two transition state, one intermediate. And what is the intermediate? The intermediate is carbocation. But when it is single state, there is no single step. There is no intermediate and you are getting only one transition state. And here I will draw the energy profile diagram for SN1 and SN2 once again. So if it is SN2, it is single step, and the energy profile diagram, it is comparatively simple. So this is the start initial position, this is the final position, and this is transition state, which is high energy state, and the gap between these two, that is the energy gap between these two, that is actually the activation energy. And there is a single activation energy because you have only single step. But if it is SN1, now we know there are two steps, and the first step is slow step. So for the first step, activation energy will be high, and this is the initial position, this is intermediate, and finally you are getting product. So this is TS1, the first transition state. This is TS2, the second transition state. This is the position of the intermediate. This is starting material, and this is product. In the y-axis, it is always energy, and x-axis, it is energy progress. So this is the difference between the energy profile diagram for SN1 and SN2. Here you have two transition state, one intermediate, but in case of SN2, you do not have any intermediate and only one transition state. Then the third point, electrophile. Now electrophile, it is nothing but Rx. If you are not comfortable with the term, then you can call it as Rx, that is alkyl halide. Here, what type of alkyl halide will give you better result? If it is 3 degree and any resonance stabilized, then it is best. It will give you best result. So not only 3 degree, if you have any resonance stabilized carbocation, because ultimately the intermediate is carbocation, and if there is any factors present that can increase the stability of carbocation, obviously that will give you better result. So that is the reason if it is looking like this, that is 3 degree alkyl halide, here the Lg that is written, which is nothing but halogen, that is the short form of leaving group. It may be also allylic or benzylic. Now see, allylic, benzylic, both are shown together, so that is why the picture is like this. So basically when it is benzylic, it will be benzene ring, then CH2, and positive charge is here. Now benzylic position, carbocation is very stable because this positive charge, it can undergo resonance with the double bonds of the benzene ring. Similarly, if it is allylic carbocation, then also resonance is possible with these double bonds like this. So that is why if it is allylic or benzylic alkyl halide, then also it will give you very good result. And 2 degree sometimes may give good result, not always. Obviously 3 degree is better. So 2 degree is also fine, but if it is 1 degree, it is actually not, it will not undergo SN1 mechanism, it will be through SN2 mechanism. Because for SN2, now come to this side, 1 degree will give you maximum result, that is maximum product you can expect. So this is 1 degree example, CH3, CH2, then Lg, that is X. Then if it is 2 degree, it is good, but not so good. And for 3 degree, it is never. Because see, when it is 3 degrees, steric hindrance is very high. And why we consider steric hindrance mostly in SN2? Because in SN2, as it is single step reaction, the nucleophile, it is, the halogen, it is still attached to R. And under this condition, nucleophile is attacking from the back side. So obviously here steric factor is more important compared to the SN1 mechanism, because in SN1, first this Rx bond is broken, you get R plus, and then nucleophile is attacking either from back side or front side. So compared to SN2, obviously here steric hindrance problem is not so significant, right? So that is why we mostly talk about steric factor only in case of SN2. So in SN2, maximum result will be given by 1 degree, then 2 degree, and 3 degree. It is not at all a good substrate for SN2. 3 degree is actually good substrate for SN1. Next point is nature of nucleophile. Now nature of nucleophile, even if it is very, suppose the nucleophile that you have taken, it is not very good, it is weak, not strong, then also it is fine. Because if it is strong, there is a chance that it will go through SN2. Now the reason is in SN2, if you look at the rate law expression, here nucleophile concentration is mentioned, but in case of SN1, there is no nucleophile concentration. So nucleophile, it is strong, that will matter only in case of SN2. So that is why in SN1, weak nucleophile is also fine. But in case of SN2, you have to take some strong nucleophile. Better if you take some anionic nucleophile, because anionic nucleophile, just take the example, suppose you are using any alcohol as nucleophile. So this is not anionic, right? You have only lone pair over oxygen. But suppose if you remove this H and if you are taking the sodium salt of this alcohol, then it is RONA. So now you have some anionic cationic nature. This is RO minus and this is plus. So there is charge separation present. So now it will be anionic in nature and you have fully formed negative charge. So now it is stronger nucleophile compared to ROH, because in ROH also you have electron density, but that is in terms of lone pair. It is not fully developed negative charge. But in case of RO minus, you have fully developed negative charge. So that is why it is better nucleophile. So if you take this type of nucleophile, it is good for SN2. And here steric problem matters. Then the next point, number 5th, what kind of solvent you will take? You should take polar protic solvent if it is SN1, and if you want to do SN2, you have to take polar aprotic solvent. Some examples are also there. What is protic solvent? What is aprotic solvent? That we have already seen in last class. So in both are polar. So polar nature is common, but protic means here hydrogen must be attached to some electronegative element. So see, in water H is attached to oxygen, alcohol also same, carboxylic acid also same. Okay, so these are the examples of polar protic solvent. This type of solvent you can use for SN1. But when it is aprotic, now see, here you will not find in any of these molecules, because all these 4 molecules are basically examples of polar aprotic solvent, and here you will not find that hydrogen is attached to any electronegative element. See, here hydrogen is attached to carbon. Hydrogen attached to carbon. Here also hydrogen attached to carbon. Here also carbon. So hydrogen is not attached to oxygen or nitrogen or any other electronegative element. So that is why it is not active hydrogen and it is aprotic in nature. Okay. So this is the comparison between SN1 and SN2. So any of these 5 points, if you have any problem, please mention. I will repeat it once again. So is it fine or should I repeat it once more?
No doubt, ma'am.
Next, we have a problem here. Ammonolysis of alkyl halide. Now, what is the meaning of ammonolysis? Here, ammonolysis means the nucleophile that you are using, that is ammonia. That's it. Okay. So, ammonolysis of alkyl halide, it means you are treating alkyl halide with ammonia molecule, followed by the treatment with NaOH. Can be used to prepare primary, secondary, or tertiary amine. So, you have started from some RX and you are ending with amine. So here I am drawing RNH2, which is 1 degree amine, but you can also get 2 degree amine or tertiary amine, 3 degree amine. So in this reaction, obviously you are using ammonia, but see, it is written followed by treatment with NaOH. So the question, it is mainly asking that what is the purpose of using NaOH? Why you are using NaOH? The reason you have to find. So 4 options are given. The first option is saying to remove the basic impurities, then to activate ammonia that is used in this reaction because it is ammonolysis. Then the third option is to remove acidic impurity. And the last one, to increase the reactivity of alkyl halide. But if we want to know which option is actually correct, first you have to understand the reaction. Now look at this reaction. It is true that the third option is correct, but why the third option is correct? Here we have taken the alkyl halide RX, you are treating it with ammonia, and here NH2 is attached to R. So one H from ammonia and X from RX, that will make HX. So this is the side product. HX is also formed. Now the RNH2 that you have obtained after the first step, this is 1 degree amine, but this is not end of the reaction, because RNH2 that can also act as nucleophile. So this is basically potential nucleophile. So now RNH2, as if it is derivative of ammonia, so it can attack another molecule of alkyl halide. So now two R groups are there, one H is removed, you are getting another HX as acidic impurity. So this is basically acidic impurity, right? And then the third step, now this is R2NH, which is 2 degree amine. This is actually the nucleophile. So this nucleophile now again attacking this R, another HX will be removed and you are getting 3 degree amine. Okay, and so in this way you are getting primary amine, secondary amine, tertiary amine, and sometimes if RX is present in excess, then this R3N also can attack as nucleophile. So now see, here 4 R groups are attached to ammonia. This is actually known as quaternary because now it is salt. Nitrogen can have maximum 3 bonds, but now it is attached to 4 R group, so 4 bonds present. That is why it is now positively charged, and X minus that will be behaving as counter ion. Okay, so these are the possibilities, but remember in each step you are getting some acidic impurity. HX is formed. So if it is suppose RBr, you will get HBr, 3 molecules of HBr for first 3 steps. So we know that according to Le Chatelier principle, if somehow you can remove the side product or impurity, basically here in the question it is mentioned impurity, but this impurity is nothing but side product. So if somehow you can remove the side product by using some reagent, then obviously the equilibrium will be shifted from left to right, and that we actually want, because now product amount will increase, yield will increase. So that is why we are using in this reaction not only ammonia but NaOH we are also using, so that it can react with this HX which is formed in each step, and ultimately equilibrium can be shifted towards right hand side. So that is why option 3 is the correct option. But why the other options are not correct? The first option is saying to remove basic impurities, but we do not have any basic side product here. So how it can be correct? Then the second option is saying to activate ammonia, but ammonia is already a good nucleophile and it cannot be activated by NaOH because both are basic in nature. It is not possible at all. And the fourth option is saying to increase the reactivity of alkyl halide, but NaOH is not such a reagent which can be used to activate alkyl halide. So that is why this is also not the correct option. So correct option is option 3. Okay, any doubt?
No, ma'am.
Now the next question is related to energy profile diagram. Remember, we already have seen the energy profile diagram both for SN1 and SN2, but in this question it is asking which of the following potential energy diagram that is representing SN1, okay, not SN2. So 4 different graphs are given in option 1, 2, 3, 4, where in x-axis you have reaction progress and y-axis it is always energy. In this case it is written potential energy. Fine. So what is the difference in all these diagram? But as it is SN1, first you have to understand the mechanism for SN1, then only you can answer it correctly. So for SN1, what we know? First, there is cleavage of Rx and you are getting carbocation. And in the second step, which is fast, this is slow. And this is RDS, rate determining step. Now nucleophile is attacking, you are getting RNU. Now as there are 2 steps, so obviously 2 transition state will be there. So for the first step, as here activation energy is high because it is slow step. So activation energy, I am writing it as AE. Activation energy for the first step, AE1, it is greater than activation energy for the second step. Okay, because the first step is slow step. Suppose if the second step is slow step, in that case activation energy for the first step will be lesser than the second step. But in this case, it is slow for the first one. So the first activation energy will be high. And obviously there will be two humps. But see, in option 4 there is only one hump. So this type of graph is actually for SN2. So this cannot be the correct option. So easily you can nullify it. But in all options 1, 2, 3, there are two humps. But there is difference. If you look at option 2, both are having same energy. It is following same line. So this is also not correct. Now among 1 and 2, what is the difference? For the first one, see if you look at this difference and this difference. Obviously the first one is high. But if you look at option 3, now the activation energy for the first step and activation energy for the second step, obviously the second one is high. So the transition state for the second step is high, but for one it is low, and this is not possible because here first step is slow step. So the activation energy for the first step should be high. So see here transition state is high. Suppose this is number 1 transition state, this is 2. So 2 is slightly lesser than 1. So that is why this is the correct energy profile diagram for SN1. Okay. So is this clear? The second problem.
Yes, ma'am.
The decreasing order of reactivity of the following organic molecules towards AgNO3. Now we are discussing this problem after finishing SN1, SN2. So obviously you can easily understand that it will be related to SN1, SN2. But suppose when you are that is in examination hall, when questions from all the chapters will be there, then you have to understand that this question, it is from related to what chapter, that you have to understand, to what topic mainly. So see, all the molecules that are given in option A, B, C, D, there is a common factor. And what is the common factor? All are basically haloalkane. That is alkyl halide. So if it is alkyl halide and you are treating it with AgNO3, now you may think that there is no nucleophile, then why it will be nucleophilic substitution reaction? But see, it is true that there is no nucleophile, but there is Ag plus. AgNO3 means there is Ag plus ion obviously present, and Ag plus can easily react with Cl minus and it can form AgCl precipitate, and Cl minus is present in all these molecules. So if there is ionization for all these carbon chlorine bond, if ionization is occurring, you can get in the medium Cl minus and then AgCl precipitation is possible. So this is also one kind of that is, you can find some similarity with the mechanism of SN1 basically, because here Cl minus must react with Ag plus, and Cl minus reacting means what? The carbon chlorine bond must be broken, then only you can get carbocation intermediate and Cl minus, and this Cl minus can react with Ag plus and forming AgCl, and this is the actual reaction. Now CCl bond is breaking, you are getting some carbocation. So basically, if you want to know the order of reactivity, whether it is decreasing or increasing, whatever it is, if you want to know the order of reactivity, you have to understand in which case carbocation will be maximum stable. So this is as if the question is actually asked in indirect way, but actually the direct question is, you have to find the stability order of the carbocation that you will be getting from all these haloalkanes after the cleavage of carbon chlorine bond, because SN1 reactivity that is directly related to the stability order of carbocation. Better is the more is the stability of carbocation, more will be the overall reaction rate. So here what we will do, we will try to find out in which case the carbocation is stable, maximum. So we will find out the order of stability of the carbocation. So for the first molecule, which is cyclopropene, and there is a CC double bond, so I am calling it cyclopropene. And you are getting, after CCl bond cleavage, you are getting carbocation. Now this is aromatic in nature, and when any species is aromatic, that process is highly facile process. But why it is aromatic? Because the criteria for aromaticity, all these criteria are fulfilled here. What are the criteria? It must be cyclic. So it is cyclic. It must be planar. It is planar. There must be conjugation present. See, conjugation is possible here. If the double bond is shifting, the new resonance structure that you will be getting, now the double bond is here, positive charge is here. The double bond can be further shifted here. You can get another structure. So these are the resonance structure. So it is cyclic, it is planar, it is undergoing conjugation, and the most important criteria, number 4 point, is that it is following 4n plus 2 pi electron rule. So here total number of pi electron, as you have only one double bond, so total number of electron is 2. So this is actually following this rule, because when n value is 0, it will be 4 into 0 plus 2, that means 2 electron. So in your case, it is 2 pi electron. So that is why it is aromatic, because it is following all the criteria for aromaticity. So obviously this carbocation is very stable. But option B also similar kind of molecule, only difference is now you have OMe group. Now OMe group, as it is donating, so it can also stabilize the positive charge when it will be at this position, because here resonance is possible. If the double bond is shifted here, new positive charge will be generated here. So now it is not only aromatic, but there is a second factor, that is now the positive charge is further stabilized by the lone pair of OMe, because this type of electron donation is possible. The positive charge is adjacent to OCH. So compared to A, B will give you better result. Both are aromatic, but in B you have some extra factor present. So B must be giving better result compared to A. Now when B is greater than A, that you can find only in option 4. Because in option 1, A before B, option 2, 3, A before B. So only this much information is enough to understand which option is correct. It is option 4. So even you don't have to consider C and D. So just be very careful. Sometimes it is not that you have to go through all the options, and in this way you can save your time also. But here obviously we'll see why C and D is after B and A. Now in C and D, no question of aromaticity, because it is not cyclic. So no question of it. But as it is not aromatic, so obviously aromaticity factor is present in only A and B. So A and B, it will always give you, A and B, it will always give you better result compared to C and D. But among C and D, why C comes before D? So here the carbocation you are getting 2 degree, but in case of D, see there is electron withdrawing group. So the carbocation, the next carbon, there is presence of NO2, which will destabilize this carbocation. Though this is also 2 degree, both are 2 degree, but here no electron withdrawing group present, here electron withdrawing group present, which will destabilize the positive charge. So that is why C will give you better result. And the correct option is first B, because it is not only aromatic, but it has also the Placer effect of OMe group. Then option A, because it is aromatic. Then C, because it is 2 degree. Then D, it is 2 degree, but there is electron withdrawing group present. Okay, so option 4 is the correct option. So after finishing the problem, next we'll see the factors that are responsible for that is whether you will get, what kind of product you will get in nucleophilic substitution reaction. So better I can say that what are the factors that are actually controlling the mechanism of nucleophilic substitution reaction, that whether it will be SN1 or SN2, that you can understand from these factors. So here we have total 4 factors. Nature of substrate. Nature of substrate means which alkyl halide you have taken. So what kind of alkyl halide? Though this is the general structure I am writing, but is it 1 degree, is it 2 degree, 3 degree? So depending on that you can get SN1 or SN2. Then nature of solvent, is it polar aprotic or polar protic? Then nature of entering group, which is nothing but nucleophile. So you can call it nucleophile, you can call it entering group or attacking reagent, whatever you can say. But nature of nucleophile, that whether it is statically hindered nucleophile or very simple small molecule, or is it strong nucleophile, or is it weak nucleophile. So depending on all these factors, you can get different methods. And finally, the nature of leaving group, that is the nature of halide basically. But better we say the term leaving group, because though we are discussing SN1, SN2 in this haloalkane haloarene chapter, so obviously here X will be halogen. But if you consider broad category of SN1, SN2, it is not just limited to alkyl halide. You can get some other types of leaving group also. Okay, so don't think that whenever you do not have any halogen as leaving group, it will not be SN1, SN2. No, it is not that. We are discussing it under haloalkane chapter, so that is why we are focusing on RX. But there may be any other type of good leaving group also. Then also SN1, SN2 possible. So better if you consider the broad in broader sense. Obviously, if you say leaving group rather than X halogen, it is better. Okay. So the first point, nature of substrate. Now, when we are saying nature of substrate, basically 2 points you have to consider: electric factor, steric factor. Now, electric factor is mostly important in case of SN1, but steric factor important in case of SN2. Why is steric factor important? That I have already mentioned, because here the nucleophile is attacking the carbon which is already attached to the leaving group halogen. But if it is SN1, it is free carbocation where the nucleophile is attacking. So obviously steric effect is less compared to SN1, SN2. And if you consider electrical effect means, remember in SN2 you do not have any free carbocation, but in SN1 you have free carbocation. So here electrical factor is important. That is, if there is some groups or factors present that is stabilizing the positive charge, obviously it will be giving you better result. Because in SN1 it is all about making the carbocation more and more stable as much as possible. So that is why electrical factor is important in SN1. So first we will see nature of substrate. What is in case of SN1? So here electrical effect is important compared to steric effect. And the reason is rate determining step is the formation of carbocation. So more is the stability of carbocation, better will be the overall reaction rate. So see, here we have taken some alkyl halide. The first alkyl halide, carbon with which halogen is attached, that carbon is attached to 3 more groups. So that is why it is 3 degree or tertiary. It will give you better result than the next one, which is 2 degree. Why it is 2 degree? Now the carbon, it is attached to only 2 more carbon, because this is hydrogen. And the next one, which is giving less better result compared to 2 degree, that is 1 degree, because now the carbon is attached to only 1 carbon. And there is another possibility, if the carbon with which halogen attached, if it is not attached to any carbon. See, here we have 3 hydrogen. So this is basically the simplest structure possible, methyl halide. So it will give you even better result than, even lesser yield compared to 1 degree. Basically, when it is SN1, maximum up to 2 degree you can get some result, but if it is 1 degree, it will now undergo SN2, and if it is methyl halide, obviously SN2 is highly preferred. So mainly it is important for 3 degree and to some extent for 2 degree also. Some more examples of carbocation is there. That is carbocation stability order. If you have proper idea, you can easily answer different types of question, because question related to that, find the SN1 reactivity order, that is very common. So SN1 reactivity order, basically you have to check the carbocation stability order. So you should have proper idea about the carbocation stability order. Here in this box we have 10 to 11 types of carbocations present. Now the maximum stable carbocation C, here C plus, that is attached to 3 cyclopropane ring. Now if you are thinking why this is so stable, now this is stable because of a special kind of resonance which is known as damping resonance. So here what happens, this CC bond is broken and this CC bond, now it is shifted here. So as if now it forms a 4-member type of ring and new positive charge is generated at this carbon. Okay. So remember, higher is the number of cyclopropane ring attached to the carbocation, better is the stability. So that is the reason it will give you better result compared to the second one, because in the second one you have 2 cyclopropane ring attached to C plus, and the third group is carbon is attached to hydrogen, and the next one, now carbon is attached to 2 hydrogen. So lesser is the number of cyclopropane ring, gradually the stability is also decreasing. Okay. So cyclopropane ring compared to benzene ring, it is actually giving you better result. See, even presence of 1 cyclopropane ring compared to 3 phenyl ring, it is giving you better stability, right? After that we have 3 benzene ring, so it is stable because of resonance with the double bonds of benzene ring. Then the next one, here we have 2 phenyl ring, 1 hydrogen attached to carbocation. This carbocation. Then the next one, now 3 methyl groups are attached. So you will have, now it is not resonance, but class I effect is possible, and also hyperconjugation effect. Next one is only 1 phenyl ring. So this is basically PHCH2. You can also call it benzyl carbocation. Then we have allyl carbocation. After that we have isopropyl carbocation. 2 methyl groups, 1 hydrogen. And the next one is CH3, CH2 plus, which is ethyl carbocation. And the last one, which is minimum stability, is CH3 plus. Obviously there is no stabilizing factor and is the least stable. Okay. So in this table you can find the carbocation stability order. So any of the species, if it is present in the options, and if the question is such that which one find the order of reactivity in case of SN1, you can easily choose the order, and you can also get the idea about the order of SN1 reactivity rate, that is overall rate of the reaction. So in this slide, is there any doubt? Next we'll see that same thing, but now it is for SN2. But for SN2, as we have already seen, that steric effect is now important, not electrical effect, because there is no carbocation, so no question of carbocation stability. So compared to the initial state means Rx, the central carbon does not become more negative or more positive in the transition state. What is the meaning of this line? So just think about SN1. When you have initial state, it is Rx, and after the first step you are getting some carbocation R plus. So R and X, that bond is broken. But when it is SN2, here it is single step reaction, and you have the transition state. Transition state, how it is? Where the bond between R and X, it is just it is not fully broken, but it is just in the stage of it will break after some time. And the bond between nucleophile and R, this is the transition state. I'm using the double dagger sign. So see, the bond between nucleophile and R, it is also not fully formed. So there is no fully developed positive charge or negative charge. So better you can write here as partially negative charge. and partial positive charge over R. So fully positive charge or negative charge is not present in TS, but in case of SN1, there is fully developed positive charge present. So compared to initial state, the central carbon is not becoming more negative or positive. There is slight polarization, that's it. But compared to initial, and that is the reason electrical factor is not important. But come to the second point, compared to initial state, now steric crowding increases around the central carbon in TS, because now this central carbon, it is having both sides, there is some groups attached to it. So compared to initial state, now in the transition state, steric crowding is increased. And here I have written it in very simple way, but if you consider the actual molecule, suppose if it is ethyl radical, better we take methyl for simplicity. Then the bond between carbon and suppose the halogen is Br, and carbon is also having 3 hydrogen and nucleophile is here. So see, now surrounding carbon there are basically 5 species. So that is, it is so sterical, right? So that is the reason now you have to consider the steric effect here. So as steric effect is important, so we will check the relative rate in SN2. So if it is methyl halide, see CH3 then X, the rate is very high, 30. Nucleophile is attacking from the opposite side. Now one of the hydrogen you have replaced with methyl group. So obviously steric crowding is increased. Now the attack of nucleophile, it will be comparatively difficult. So that is why the rate is decreased from 30, now it is 1. So just addition of one methyl group is drastically changing the rate. Now in the third case, another methyl group you have attached. More sterically hindered, now the rate is 0.03, lesser than 1. So this is methyl halide, this is 1 degree, this is 2 degree. And the fourth case is very interesting because here carbon with which halogen is attached, that is attached to 2 hydrogen and 1 carbon. So this is actually 1 degree. Though it is 1 degree, but still because of this presence of CMe3 group, this is basically CMe3 group, tertiary butyl group, it is taking a huge space. So the attack of nucleophile from this, see, this is very narrow space here, it is highly difficult. And that is why now the rate is drastically decreased compared to 0.03. So though it is 1 degree, but still it is not giving you good result because of the steric hindrance. And this group is known as neopentyl group. Neopentyl group is Me3C CH2. This is neopentyl group. Fine. Pentyl means total number of carbon C, 3 carbon, 1 carbon, 1. That means total 5 carbons. And neopentyl group, after that we have the next species which is 3 degree, because now carbon is attached to 3 methyl group. So here also nucleophile, it is facing problem, and even compared to nucleophile, it is giving you almost 0 rate. So basically 3 degree, it is not at all suitable starting material for SN2. If it is 3 degree, it is actually give nucleophilic substitution reaction through SN1 mechanism, not SN2. So for SN2, it is a cross sign. Okay. Now some alkyl halide molecules are given here, and you can compare their order of reactivity in SN1 and SN2. So first see in SN1 what kind of substrate we have taken. Maximum yield you can expect from 3 degree halide Me3CX. Then the next one is PHCH2X, that is phenyl halide. So in this case, why it is giving you better result? Because carbocation is highly stable. After that you have allyl halide. Here the carbocation is like this. Then you have Me2CHX. This is 2 degree isopropyl halide. And this is ethyl halide, this is methyl. So as you are moving towards right hand side, gradually the rate is decreased. And when it is SN2, PHCH2X is giving better result than allyl halide. Now, if you compare steric hindrance, both are actually, there is no such steric problem, because carbon with which halogen is attached, that is actually 1 degree. So this is also 1 degree, this is also 1 degree. But if you think that why it is mentioned resonance stabilized, because resonance, that question arises only when it is carbocation, right? But remember, though it is not forming fully developed positive charge, but still there is some partial positive charge present. Simply take this alkyl halide. So when you consider SN2 transition state, CH2, and the bond between carbon and halogen, it is just broken. So some partial positive charge is there in the starting material, sorry, in the transition state. So these partial positive charge can also be stabilized by this resonance. So that is what is mentioned, resonance stabilized. So these two, whether it is SN1 and SN2, in both cases it can give you better results. See, this PaCH2X and allyl halide, it is present in SN1, SN2 also. And after that, CH3X will give you better result. After CH3X, it is ethyl, because this is there is only one methyl group. Now another hydrogen is replaced by methyl. So sterically compared to CH3X, it is more hindered. So as we are increasing the number of methyl group, stability is decreased. And CH3CX, which is giving you maximum yield in case of SN1, because it is present at first position. Here it is present at last position, because for from the steric point of view, it is not at all a good substrate for SN2. But these two substrates are very unique, because these two substrates are such that can give you better result both in SN1 and SN2, because they are not only less sterically hindered, but they are also stabilizing factor present. Okay, so this is all about the nature of the substrate. That is the first point. After that, nature of solvent. Now when we are saying solvent, in both cases we are taking polar solvent. We never take non-polar solvent. Now why we never take non-polar solvent? The reason is that here starting material is Rx, right? And this has some amount of polarity. So when you are doing this reaction, suppose if you have taken any non-polar solvent, suppose you have taken CCl4, which is non-polar solvent, and you are dissolving this Rx in CCl4. But solubility will not be very good, because Rx has some polar nature. Halogen is electronegative. So the carbon halogen bond is polar. There is some polar nature in this molecule. So obviously it will prefer some polar solvent, not non-polar solvent. So that is why we never talk about non-polar solvent. Now under polar, two possibilities are there. One is it polar protic or polar aprotic? So if it is polar protic, it will be mainly for SN1, and for SN2 it is polar aprotic. So the feature for polar protic solvent, there is active hydrogen present, so it can donate H+. See, examples we have taken water, then methanol, CH2OH, ethanol, acetic acid, or any other carboxylic acid. But if you look at the examples for polar aprotic, so these are the polar aprotic solvent: tetrahydrofuran, cyclic ether. Here hydrogen is attached only to carbon, but not attached to electronegative element oxygen. Then we have acetone, then dimethyl formamide. So these two are basically methyl group. Dimethyl form amide, because this is actually amide molecule. Amide molecule is amide means what? CONH2. But here NH2 we don't have, but we have NR2, NMe2. So this is also amide. So it is dimethyl formamide. And formamide, it is basically coming from the one carbon, because it is actually formaldehyde. Formaldehyde is HCOH, and formamide, that structure is HCO NH2, and dimethyl formamide is when you have replaced both the hydrogen by methyl. So that is, it is known as DMF. So the short form and the full name, both you should know, because in question mostly these short forms are used, TMF or THF, but this is the actual structure and the full name they are also mentioned. Then MECN, acetonitrile, this is methyl group, and dimethyl sulfoxide, DMSO. So all these are examples of polar aprotic solvent, which are mainly used for SN2. Okay. Now, if we consider ionization power of solvent. Now, what is ionization power? Ionization power means, just take this example, Rx. In case of SN1, what happens? It forms R plus and X minus. So this is actually ionization. So if the solvent is having good ionization power, that means it will assist in the cleavage of Rx bond breaking. Okay, in the cleavage of Rx bond. So that is the ionization power. So higher is the ionization power, easily you can get R plus and X minus. Now this ionization power of solvent, that is dependent on two factors. One is dielectric constant. Higher is the dielectric constant, better will be the ionization power. And the second point is solvation power. Fine. Now here we have this table where you can find the dielectric constant values at 20 degrees centigrade for all these solvents. So this chart, if you carefully observe, see, maximum value you can find, it is for water, which is almost 80. So that is why water is so polar compared to all these other solvents. Then for alcohol also it is very high, see 32. Formic acid HCOOH. For carboxylic acid it is high. But if it is formic acid means HCOOH. But if this H is replaced by methyl, now it is acetic acid and it is drastically decreased. So the polarity of formic acid, it is very high compared to acetic acid. Then ethanol, these two are comparatively close. And see here, dimethyl formamide, its value is also high. So that is why it is also very polar in nature. Okay. But other solvents, as you can see, acetone or chloroform or toluene, their dielectric constant is very, very low. Okay. So higher will be the dielectric constant, more will be the polarity, and when polarity is very high, ionization is also very high. Okay. Next we'll see solvation effect. And when we will discuss solvation effect means the solvent will have some feature that will stabilize the positive charge or negative charge, that is cation or anion. Now here we have taken the solvent DMSO. Remember the structure of DMSO? CH3 S double bond O CH3. This is polar aprotic solvent. And here, suppose you are doing the reaction Rx in presence of KCN. Now KCN is basically source of Cn minus, which is the actual nucleophile, and you will be getting RCN as product. So if you want this reaction that is better yield for the product, the nucleophile must be in free condition. So the cyanide ion, it must be relatively free. So the solvent should be such which will stabilize only the positive part, not the negative part of the reagent. Then only it can remain in free condition. See, there is no stabilizing factor from solvent. It is completely free and it is very good nucleophile. And here K plus is surrounded by, here 4 molecules are shown for simplicity, but there may be more than that also. And all the oxygen atoms of DMSO molecules, they are facing this K plus, because oxygen site compared to sulfur, it is more electronegative. Oxygen is more electronegative than sulfur. So if you consider the polarity of sulfur oxygen bond, obviously it is del negative, this is del positive. And del negative part, that will be facing this K plus, which is the positive part of the reagent. And we want this Cn minus to be in free condition. And here the solvent is such. Here stabilizing this negative charge is not possible by the solvent. Because see, here positive charge is present here. But this part is not, it is from the structure you can understand, it cannot interact easily with Cn minus. But compared to that, oxygen side is free. It can easily stabilize the positive charge present over potassium. But Cn minus is free because it is not getting any positive stabilization from the solvent. Okay. But when it is polar protic solvent, for example, if you have taken water, now you can see R3X, if it is broken and if it is SN1, you will want this to be stabilized, and this is getting stabilization from the oxygen side of water molecules. So oxygen, as it is the negative part of the water molecule, it is facing this positive charge, it is stabilizing it. And when it is a negative one, suppose if X is Br minus, that is also getting some stabilization, but now the hydrogen is facing Br. So in this way, it is stabilizing both cation and both anion. So that is why polar protic solvent is used in case of SN1, but polar aprotic solvent used in case of SN2. Because in SN2, you want the nucleophile to be in free condition, but not in SN1. In SN1, it is not necessary that nucleophile must be in free condition. Okay. So some more factors we'll discuss in the next class. So until this slide, is there any doubt? So as there is no doubt, we are ending the session here. Thank you for listening.